In this video, I am going to explain the theorem. If E is a link of G, then tau of G is equal to tau of G minus E plus tau of G dot T. So here they are talking about a graph G, and for this graph G, there is a link, and link means edge. They are talking about edge. Okay, so in the graph G, we have an edge E. Then if it is like that, then tau of G means number of spanning trees in the graph G. That is what mean by this tau of G. Okay, so what is tau of G? Number of spanning trees of G will be equal to number of spanning trees of G minus E plus number of spanning trees of G dot T. Okay, so here what they are talking about, if there is a graph G, okay, if there is a graph G and using that graph you are drawing so many spanning trees. Okay, so they are saying the number of spanning trees you get from the graph G will be equal to, here what, this is the graph, and the graph, in this graph there is no edge E. It means E edge is not there. Okay, some other edges will be there. They are talking about E edge. This particular E edge is not in this graph. So that is why this graph is denoted as G minus E. Okay, so and this is what is mean by G dot T. It means, here you have a definition for G dot E. I will show you. Is that visible? Yeah, G dot T. Okay, so here it's a case an edge E of G is said to be contracted. It means this G dot E means this E is getting contracted in the graph G. Okay, so I will show you how. Okay, if the edge E is contracted in the graph G, then you denote it as G dot E. So here I will show you how it is contracted. Have a look at this figure. Okay, this is a graph G and this is G dot T. So in this graph G, here it is an edge. So this edge E is contracted. It means this edge got deleted and the two end vertices will get joined, so that the figure forms like this. Okay, this is mean by G dot T. Okay, so here in our proof, in our theorem they are asking us to prove number of spanning trees of G will be equal to the sum of this two, that is sum of number of spanning trees of this and this. Okay, so for that what you are doing is, first in the first line of the proof you are writing what is given in the statement. So given G is a graph and E is a link of G. Okay, link of G means E is an edge of G. So here after that you are considering a spanning tree, that is what, capital T. Let T be the spanning tree of this graph G. Now consider a graph G that does not contain E. So imagine a graph, and for that graph does not contain E. Okay, for example, I will draw a figure. Here is a graph. Okay, in this graph you are not having edge E. Okay, so when you draw spanning tree for this graph, what will happen? What will happen? In the spanning tree also you don't have that edge E, right? So that is what I have written here. Consider a graph G that does not contain E, then the spanning tree T of G also does not contain E. Okay, therefore tau of G minus E means what? The graph that does not contains E. That is what mean by G minus E graph. So tau of G minus E means number of spanning trees of this graph G minus E. Okay, it means is the number of spanning trees of G that does not contain E. Okay, just now I explained, and that is in the that is here in this line, right? Tau of G minus E is the number of spanning trees of G that does not contain E. Now, each of the spanning tree T that contains E, there corresponds a spanning tree T dot E of G dot E. That means they are saying that if you consider a graph G dot E, okay, a contracted graph, that is G dot E. This G dot E, imagine in this G dot E there is an edge, particular edge. When you draw a spanning tree for this G dot E, then that in the graph G dot E have that edge, particular edge. So in this spanning tree of G dot E will also have that particular edge, right? So that is what they are saying. Each of the spanning tree T that contains E, there corresponds a spanning tree T dot E of G dot E. This correspondence is clearly a bijection. Why they are saying this as a bijection? The reason is because you can consider the graph G as one set and the spanning trees at other set. Okay, so if in the graph G if there is the edge E, then in the spanning tree also there is an edge E. In the graph if there is no edge E, then in the spanning tree there is no edge. So all the elements in G having image in where? The spanning trees, and all the this is domain and this is codomain, right? When you talk about mapping, this is domain and this is codomain. So all the elements in codomain will have pre-image in the domain. Okay, so that is what bijection usually. So here in this story that we have learned just before, having the correspondence bijection, and this correspondence is clearly a bijection. So therefore we are saying that tau of G dot E is the number of spanning tree. In G dot E we have what? E, edge. That is what we have wrote here. Tau of G dot E, everything is our assumption, and finally you are coming to an conclusion. So therefore tau of G dot E is equal to number of spanning trees of G that contain E. Therefore we get this. Okay, this is what they are asking us to prove. So finally you got that. Here you have to think about something logically. So here tau of G, right? Imagine the number of spanning trees of this graph G will be equal to, here in this graph you will have that E, right? But here you are eliminating this edge E. So here you are not having that E, but here you have that E. Okay, so the number of spanning trees of G you will have that edge E. Here you don't have that E, but here there is an E. So anyways, when you add this two, you will get that E, right? So finally the number of spanning trees of G will be equal to the number of spanning trees of these two. Sum of these two. Sum of the number of spanning trees of these two. This is how the theorem comes to an end. So hence the proof.